Hey guys, so I want to slowly bring this Vellum series to a close, and I thought a neat way to do that would be with a production setup, which came out of a project I did where I had to art direct and control a peel-off effect. So let's build that by dropping down a font here, diving in there, and let's just use a simple N for now, and set the font to maybe Chivo Black Regular. Let's extrude this using a poly extrude, and maybe let's extrude this 0.15 units. Let's leave the output back unchecked so we have an open geometry here, and then drop down a transform. And I want to rotate this minus 90 degrees so it sits flat on this plane here, like so. Next, let's remesh this to generate our simulation mesh using the remesh SOP. And I want to use all input edges as hard edges so they don't get mushed around. And let's use a target edge length of 0.03 with, let's say, a high iteration count, 32. So we get a very uniform mesh like this. Also, I want to copy these two nodes here and paste them over here. And in this one, the poly extrude, check the output back. So when I highlight the transform here, we now have an enclosed geometry. And I want to feed that into a VDB from polygons, because what I'll do here is I will build a collision geometry that's shrinked a bit, so it doesn't collide initially. I'm going to use the VDB from polygons here. Let's just dial back the voxel size to something really small, say 0.0025. And also I want to increase the exterior and interior band voxels to say 8. Next I'm going to use a VDB reshape SDF, which I'll set to erode this letter N. And let's just ghost our initial letter here and see how the erosion offset manipulates our geometry. Let's set this to something rather big, say 8. So now I see I don't have any geometry parts of my original geometry intersecting with the VDB that I just built. Let's convert this back to a polymesh using the convert VDB, set to polygons, and in here this is a bit dense for my taste, so I'll crank up the adaptivity to say 0.1, and that seems good. Alright, let's just save this, and let's set up our Vellum constraints by highlighting this remesh node here and dropping down a Vellum cloth constraint, and also a Vellum solver. Let's highlight the Vellum solver and increase the substeps while decreasing the constraint iterations to say something like 10. And also in the forces tab I want to disable the gravity and instead have a bit of wind blowing along the z direction, so maybe 3 units in the z direction and 4 in the y direction. So we're blowing this cloth here diagonally upwards. Let's just simulate this. Well, not much to see here. This cloth just lifts up without even intersecting with our underlying geometry. So let's take care of that by just directly feeding this collision geometry into our Vellum solver. So that's my collision geometry here. And again, let's resimulate this. And now we have some slight collision happening here, where this mesh touches the N. Now what I want to do is control this peel-off effect. And for that I need constraints. Constraints that pin my simulation mesh to our original geo. For that I'll use a Vellum attach to geometry node, which I'll wire in between the cloth and the Vellum solver. And instead of this collision VDB here, I will feed in my original remeshed mesh in here. So what that will yield if we drop down a null object and attach this to our constraints here is you can see those spheres here, and those are constraints which pin our cloth to this original geometry here, the very same geometry that we're then using for simulation. Now that I created those pin constraints, I want to have them in a separate group. So down here I'll check output group, call this group maybe attach because they attach this to the original geo, and it's set to be really stiff currently. So let's just see how that looks and highlight the Vellum solver and simulate this. And you can see nothing is moving here because these constraints are really stiff. However, if we lower the stiffness here to say a value of 10 and resimulate this, we can see those constraints have a bit of give, but still keep this cloth to the original geometry. Let's reset this value here. So to control this peel-off effect, I will use some geometry, which I will animate through this mesh here. And as soon as my animated geometry comes close to any of those points, any of those constraints holding the mesh onto the original geometry, I will release those constraints. I basically will delete them. So let's do that by creating a grid, which is gonna be my geometry, which I'll animate, set the grid size to be 1 by 1, have it along the XY plane, maybe highlight it, so that's my grid here, and increase the rows and columns count to say 100 by 100, like this. Next I'll just animate this, so the first frame I'll set it to say minus 0.6, set a keyframe by alt-clicking in there, and then maybe going to frame 96, I'll move it to plus 0.6, set a keyframe again, alt-click in here, and by shift-clicking I will open up my F-curve, my animation curve editor. Just highlight this animation curve here and make it linear. So now I have just a linear motion of this grid wiping through my geometry. So to release those constraints that are in the attached group here, I will dive into my Vellum solver, and in here I'll drop down a GeoWrangle and set this up to work on the constraints, which is done under the Data Bindings tab. And in here, instead of binding the geometry, I will bind the constraint geometry. And as for the inputs, input 1 should be just myself, no reads of outputs. And for input 2, I want to input this grid that I just animated. So I'll set this to a SOP, and then in a SOP path, I will navigate to my grid that I'll animate it here and select that. All right, I want to have this only run over the attach primitives, so the attach constraints, which I put in the attach group. For each of those primitives, and let's set this to primitives, I want to check if we have points nearby from that grid. So I want to find near points, so NPT is just the integer variable in which I'll store the point number of the closest point that I'll find. And I'm going to use the near point function on the geometry coming in through our second data binding. Again, the second input here, that's this one, the grid, has the ID 1. And I want to look from the current primitive's position. And then I want to check if we found something. So if near point is returning something that's bigger than -1, because if near point didn't find any points nearby, it will just return -1. So if NPT is bigger than -1, we'll do something. In our case, we will delete our primitive. The primitive, that is the constraint that's attaching this geometry to the original geometry. So remove my primitive on the current geostream with the current prim number. And I want to delete the points of this primitive too. However, this will now always or immediately delete all those primitives because we didn't restrict our near point search to a given distance. So instead, let's set this to a distance of, say, 0.1, like this. Okay, let's go up one level, save this. Fingers crossed, let's highlight our Vellum solver here and maybe pipe in the constraint stream here in the null so we can see what and if something's happening. And also let's ghost the grid. And let's simulate this. So that seemed to have worked. Let's reset this, highlight the Vellum solver, and let's replay this. So yeah, that's working. Except for one thing, that we now again lost the original collision geometry that we prepared, this thing here. So let's wire that back into the Vellum solver and resimulate. Alright, that too seemed to have worked. So let's reset this. And so what would be nice is kind of this surface lifting a bit or getting released before it completely detaches from the original geometry. Basically, I want to set up a second grid that wipes through this letter before this grid, which releases all the constraints. And what the second grid should do is just decrease the stiffness of those constraints, keeping the cloth onto the original geometry. Basically, what we want to animate is this stiffness value here. And if we go to the geo spreadsheet here with our Vellum attach highlighted and set it to Vellum constraint geometry, go to our primitives here and select everything that is in the attach group here. And we can see we have this very high stiffness value here, which is set to be this value. So basically what we have to do is set up a second animated grid here. Let's just copy this one, use that. Maybe delay our first grid a bit by shift-clicking in our animation here, and then moving those keyframes out a bit, maybe starting the animation at frame 48. Okay, our second grid, which is the grid that wipes through this letter first, should animate the stiffness or control the stiffness. So let's dive back into our Vellum solver, and within this same geometry wrangle, let's, under inputs, link up another SOP, our second grid here. Let's just copy this, paste this. Let's rename this to grid 2, like this. And in our code here, let's just copy those 3 lines here, paste them down here. Let's call this one NPT2. And what we want to check here is on the second grid, that's the one coming in through the third input, that's the one with the ID 2. If we find a point close by, then we don't want to remove the primitive, but we want to set a float value called stiffness to something low, maybe 10 in our case. Okay, let's head up one level, save this, and resimulate. Okay, that seemed to have worked, but let's zoom out a bit and replay this animation here. And what we're seeing here is that this cloth is still somehow attached to this geometry. So let's highlight the null to visualize our constraint geometry. And for some reason, we didn't delete all those constraints. So let's just watch this animation closely, what's happening here. And we can see when the second release happens, the cloth just flips away from the grid without the grid being able to come close enough to release those final few constraints here. So either I could reanimate my grid, make that go a bit faster through my geometry, or I could just in the vellum attach here, enable breaking with my constraints and set this threshold up to a certain value which catches those final few constraints. And that's a bit of trial and error here in resimulating. And in my case, a value of 0.0025 seemed to give decent results. So again, let's save this and resimulate. So yeah, now those final constraints release 2 automatically. So what you typically do now is use this simulation geometry, which is admittedly a bit coarse, to drive a high-res geometry. And we could just fake that by copying these few nodes here over there, maybe just those two, and delete the font here, and check output back again, and then I'll just create a VDB again, which I'll use to create a fake high-res mesh here. Converting this again to polygons here, and as my original sim geometry is hollow, so hasn't got a back face here, let's just use a clip to get rid of the back face here, and then let's use a point deform to drive my high-res mesh. So high-res mesh goes in the first slot, then the rest mesh, which is just what we feed into our vellum constraints here, and then our deformed mesh, that's the mesh after the simulation. So when I now skip through a simulation, I can see my high-res mesh being deformed here. And finally, what I want to do, sometimes in a simulation you get errors, especially when you render this with high gloss surfaces. And the reason for that might be normal errors. So what I want to do is, using a pointer angle, I want to blend between the standard normals of this mesh and a blurred out version of those normals, a smoothed normal version of this mesh. And I want to blend depending on how far these mesh points travel away from their original position. So let's do that, dropping down a pointer angle, and I want to compare this against the undeformed mesh position here, and then use another attrib blurred version of my deformed mesh. Just quickly highlight this, and in here I will blur the normals of this mesh, maybe for 10 iterations, so they are smoothed out like you can see here. Alright, so in my pointer angle, first I'll need to look up my original point position, which when thinking about it, we can do a bit simpler. Just slash this and instead use a rest position stop here, which will take care of creating our original points position in this attribute called rest here. So we can now wire this attribute blurred version here in the second slot, and then what I can do is compare my current point position against this rest position and measure their distance. So what I want to do is create a float, call it d for distance, and it should be the distance between my current point position and the rest point, the original point position. Next I want to create some sliders to dial in the minimum and maximum distance of our effect to remap it. So let's create a float, call it min, and use a float slider which we'll name min2. Copy this line, paste it here, and do the same thing for a variable which we'll call max. And let's call the float slider max2 and create those two interface elements. Maybe dial in a maximum value of 0.3 for now. Next, let's remap our distance and call the result of this a bias. And we will fit our distance d between our minimum and maximum float values that we dialed in, resulting in a value of 0 to 1. And finally, create our new normals by blending between our blurred and our non-blurred normals using the lerp function. However, to access our blurred normals, let's just read them using a point function. So a vector, let's call it blur n. And just as we would read in our point position, let's just read in our normal value from our second input slot with the same point number as our currently active point. Now, finally, we can blur between our current normal and our blurred normal, depending on our remap distance, which we called bias here. Alright, let's compare this to the original geo, and you can see now, in these areas that had been deformed, my normals are a bit smoother now, without those unsimulated or unmoved areas being affected that much by the blur. So again, that's just a neat hint if you're getting errors in glossy parts of your shading in highly refractive materials or highly reflective materials such as chrome or silver. And with that, for now I want to bring the Vellum series to an end. It's kind of fitting that we just have a thunderstorm outside, but if you have the feeling that there's something missing here, or that is something lacking from this series, just let us know, and we might these parts as an addendum in the future. Alright, until next week, it's cheers and goodbye.